The following program is brought to you by Caltech.
Welcome back. Last time, we discussed the feasibility of learning, and we realized that learning is indeed feasible, but only in a probabilistic sense. And we modeled that probabilistic sense in terms of a bin that has an out-of-sample performance. We already mapped that to the out-of-sample performance. The performance we don't know. And in order to be able to tell what E out of H is the hypothesis that corresponds to that particular bin, we look at the in-sample, and we realize that the in-sample tracks the out-of-sample well through the mathematical relationship, which is the Hoeffding inequality, that tells us that the probability that E in deviates from E out by more than our specified tolerance is a small number, and that small number is a negative exponential in n. So the bigger the sample, the more reliable that E in will track E out well. That was the basic building block, but then we realized that this applies to a single bin, and a single bin corresponds to a single hypothesis. So now we go for a case where we have a full model, H1 up to Hm, and we take the simple case of a finite hypothesis set, and we ask ourselves what would apply in this case. We realize that the problem with having multiple hypotheses is that the probability of something bad happens could accumulate, because if there is a 0.5% chance that the first hypothesis is bad, in the sense of bad generalization, and 0.5% for the second one, we could be so unlucky as to have this 0.5% accumulate and end up with a significant probability that one of the hypotheses will be bad. And when one of the hypotheses will be bad, if we are further unlucky, and this is the hypothesis we pick as our final hypothesis, then En will not track E out for the hypothesis we pick. So we need to accommodate the case where we have multiple hypotheses. And the argument was extremely simple. G is our notation for the final hypothesis. It is one of these guys that the algorithm will choose. Well, the probability is that E in doesn't track E out will obviously be included in the fact that E in for H1 doesn't track the out-of-sample for that one, or E in for H2 doesn't track, or E in of Hm doesn't track. The reason is very simple. G is one of the guys. If something bad happens with G, it must happen with one of these guys at least, the one that was picked. So we can always say that this implies these things, which is this or this or this or this or this. And after that, we apply a very simple mathematical rule, which is the union bound. The probability of an event or another event or another event is at most the sum of the probabilities. That rule applies regardless of the correlation between these events, because it takes the worst case scenario. If all the bad events happen disjointly, then you add up the probabilities. If there is some correlation and they overlap, you will get a smaller number. In all of the cases, the probability of this big event will be less than or equal to the sum of the individual probabilities. And this is useful because in the coin flipping case, which started this argument, the events are independent. In the case of the hypothesis of a model, the events may not be independent because we have the same sample and we are only changing the hypotheses. So it could be that the deviation here is related to the deviation here. But the union bound doesn't care. Regardless of such correlations, you will be able to get a bound on the probability of this event, and therefore you will be able to bound the probability that you care about, which has to do with the generalization, to the individual Hoeffding applied to each of those. And since you have capital M of them, you have an added M factor. So the final answer is that the probability of something bad happens after learning is less than or equal to this quantity, which is a helpful small quantity, times capital M. And we realize that now we have a problem, because if you use a bigger hypothesis set, M will be bigger, and therefore the right-hand side here will become bigger and bigger when you add the M, and therefore at some point it will even become meaningless. And we are not even worried yet about capital M being infinity, which will be true for many hypothesis sets, in which case this is totally meaningless. However, we weren't establishing the final result in learning. We were establishing the principle that through learning you can generalize. And we have established that. It will take us a couple of weeks to get from that to the ability to say that a general linear model, an infinite one, will generalize and we will get the bound on generalizations. That's what the theory of generalization will address.